Just try to go.
So you're waiting for
Block.
Still daylight savings.
I think they didn't turn on the heaters today, right? Yeah. That's not heater fighting. I nice. How was the homework?
It's easy, not bad.
All right.
It's good.
Well, okay. So does that mean that the mathematical background you need for the vector operations is all familiar?
Yeah.
Give or take, yeah. Give and take, okay. So. I want to go over that a little today, so let's begin. So the basic idea is going to be to develop some mathematical tools to do vector operations, but since we are an E&M, we also do the math, the context of Maxwell situation with it. So we have Maxwell equations again. Before that, I should say what is due, what is due. We have this homework one that was due today. And I have not yet posted the homework because I want to go over this mathematical. Stuff a little bit before I post the new homework, so probably the next homework will not be posted until Thursday also, and it will be due 1 week. From there, that's what I expect. It will be probably very close to the homework that were prepared last year, but I'm gonna give it some thought on. Okay. So, and then the midterm also is relatively far, so we don't have to bring that up. Okay. So Maxwell's equations, that is the first few of them. They look like this, so that's epsilon times E, that's equal to the charge density. That is the position and time dependence in it, which I'm not writing. What's it? And we have del started with the magnetic field. It's equal to 0. So let me stick to the divergence equations alone. What does it means to say that the divergence of a magnetic field is 0? It means that we also said the divergence means something radially coming out of a charge. So if it is 0, that means that there is no radial component to that field in a sense. There is no source to the magnetic field. We say there is no magnetic moment. This implies immediately that B has to be of the form, has to be a curve of another quantity. And we say that exists a field, a vector field if you want, whose curl is actually equal to magnetic field. This notice what is the divergence of a curl. So then that leads us to the idea that what is the divergence of a curl? What is that equal to? That's equal to 0. And why is that 0? Why is the divergence of a curl 0?
By proving
it explicitly. Doing that, that's correct. That's so maybe I can ask. So these are 3 vectors, right? What about, let's say, C dotted with B crossed with A? And this is nothing to do with magnetic field. Because it is a random arbitrary. Let me not even write B. So there is A, B, A, C, and D, let's say. A, M, and then it's some random vectors, and you take a curl of it, and then you take it that it's fields, so a curl and a divergence. Does that take it to 0?
If it's in the same plane.
If that's these are not vectors, remember, the vector fields, right?
Mm.
So yeah, so at one point, let's say if it is on the same plane, that will be
0.
0. But what about this? Does that mean that it is on the same plane?
Because curl is rotation, but divergence is inward or outward.
What sense is it rotation? I am asking, how about maybe make this better? How about M dotted with M cross A? Is that 0?
Yeah.
Right. So that's 0. What about M dotted with A cross M? That's also 0. Like, is that some? So what's it that is making it 0? I mean,
Because the product, the curl gives us a vector which is like in the 90 degree perpendicular.
makes sense, right? In this case, what about this? the gradient, or how does that come about? This gradient, how do you associate a direction to the gradient?
The direction is to
It's
the
perpendicular.
maximum difference.
If it's a scalar. Right, this is a curve. Right, so what you're trying to say is the gradient of a scalar field, then it is the maximum slope in a sense, right? Yeah, that's correct. But then you have to take a gradient of a gradient, so so what I'm trying to point out here is that all these are true statements, and most of you are getting it correct. It is the direction that is coming into picture, except that when it comes to gradient, the insight of a vectorial direction is slightly tricky. It depends on what it is acting on. Like gradients, the direction of the gradient depends on what it is acting on. Like unless it's acting on something, you don't even know what its direction is. Right? So in that sense, it is tricky to see this, or you will not be able to, if you didn't know this result first time, it's the first time you actually, as Matt said, you actually evaluate, right? Unless you do that, you don't have an insight for it to do that. One way to do that is, so let's so that was the motivation for taking the index notation. So A cross B cross C is, or let's first write B cross. The index notation for this is epsilon I j k bj and ck. Is that familiar? Index notation, mass. Okay, good. Okay, so let's go over that a little bit. So vector A, any random, so this is now we're talking about vector, not even a vector field. If we are working in ijk, so this will often be write this as A1 I hat plus A2 j hat plus A3 j hat. Right, those are three components of the vector. And if we are always going to be working in the rectangular coordinates, only if we are always working in the rectangular coordinate, then you get really lazy. It seems like that's really not necessary to write it. If it is in the background, we always say that we are always going to be in rectangular coordinates. And this is also okay to write A1, A2, A3. But actually, you lost some information in here because this is in rectangular coordinates. We stopped writing indices or the unit vectors, but it's okay as far as you stick to that notation. And then you say that, oh, I'm going to get more lazy. And I say that I don't even want to keep writing this. And you say that I'm just going to write AI. That means that there are three components to this. And it means that I is equal to 1, 2, and 3. So for when I is equal to 1, it's X component. When I equal to 2, it's the Y component. And when I is equal to 3, it's the Z component. Again, with the understanding that it's the unit vectors are always going to be rectangular coordinate. Then what can we do with it? So let's say you are doing A dotted with B. Right, that's a scalar product. We know that if A1, if there are two vectors, then you do A1 B1 plus A2 B2 plus A3 B3. And this is nothing but summation over I is equal to 1 to 3 I. That should be familiar. And now here is the notation. This is what is called index notation or summation notation if you want. You stop writing the summation. But that seems like really off because you never know when to sum and when not to sum. But the rule, the notation is it always works. If I is repeated, if an index is repeated, sum over it. If the I is repeated, so it means that I is sum, so it is, that's where the information of the sum goes. It seems like that's an unnecessary notation, which could be confusing often, but especially when you have 5 sums going on at the same time in the same equation, it takes away a lot of clutter. And once you get used to it, it's a lot more powerful in a sense. And so that's dot product. It's we also want to introduce let's say a certain quantity, let's say. This is a tensor. So let's say you have a symbol delta ij. So this is going to be called the Kronecker delta. Kronecker delta, let's say delta. So it's going to be, so now how many components does it have? Now notice all the indices. Now what we mean here is that I can go from 1 to 3. So similarly, J can go from 1 to 3. So there are how many components in here? There are 9 of them, 3 here, 3 here, so it is 9. So a good way of arranging them is delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, 3, 2, 3, 3. And it is convenient to write it in this form. This is the equivalent of this. A vector has A1, A2, A3, 3 components there. Here, there are 3 by 3, there are 9 components. So this is a tensor of rank 1. This is a tensor of rank 2. 2 indices, 2 rank. Right? This is only 1 index, 2 index. If there is no index at all, you will say it's a scalar. So this is a tensor of rank 1, which is basically a vector. Tensor of rank 2, and that's a Kronecker delta symbol. That's an example of that. In this case, now we want to make this much more a constraint Kronecker constraint symbol, in the sense that this is 1, 0, 0, 0, 1, 0, 0, 0, 1. That's basically the identity matrix. And often we will say delta ij is equal to 1 if I is equal to j, and equal to 0 if I is not equal to j. Each of this is a way of defining the Kronecker delta. So that it's an identity matrix, or it is it's a symbol, it's a rule saying that its components are 1 if I is equal to j, and its components are equal to 0 if I is not equal to j. With this information, let's consider the quantity. So AI the j times delta ij. So that's it. Now, how many indices are there in this? Like it seems like there's an I, there's a j, there's an I and a j. So let's call this a quantity C. Now, this was a vector, which means it has one index. This was a tensor of rank 2, that means it had 2 indices. And now we could ask, there are how many indices in this? So it seems like there are 4 indices, right? I, J, I, and J. And naively speaking, you would immediately say that, oh, this is a tensor of rank 4. But no, remember, we have our index notation. It says that if it is repeated, sum over it. So these are not free indices. This is actually a sum over I, right? I and I is repeated, and there is a sum over J. So I is equal to 1 to 3, J is equal to 1 to 3. After I sum them, the index is gone, right? Like for example, when I sum this out, the index is gone and I get nothing, I get a scalar basically. So a repeated index is not really a, so that we will distinguish between free index is when there is no sum and a dummy index. These are all tricks in a sense. So this contributes to the rank, contributes to rank of a tensor. This does not contribute. Okay. So again, now we ask, then what is this equal to? There are how many free index in this?
0.
0, right? So there's no free index in this. That means this is a scalar. And then you would say, oh, in what sense is this a scalar? So let's evaluate this. So I'm going to sum this up. So this is nothing but I is equal to 1 to 3, J is equal to 1 to 3, AI times BJ times delta IJ. When I sum this up, there is this very special property of the symbol that it contributes non-zero quantities only when I is equal to J. Right, so out of this, when I sum this, there are 9 pieces in here. Out of those 9 pieces, only 3 survive, which is when I is equal to J. And that means that this is A1, B1, delta 1, 1, plus A2, B2, delta 2, 2, plus A3, B3, delta 3, 3. But delta 1, 1, delta 2, 2, delta 3, 3 is 1. So that's nothing but A1, B1 plus A2, B2 plus A3, B3, which is nothing but A dotted with B. So in a sense, what we have done is actually, if we were interested in A dotted with B, we inserted a 1 there. If you want to think of it in terms of matrices. So a matrix or a tensor of rank 2, I'll use a double vector for that. Okay, so this is a notation now. This is a Kronecker delta in matrix notation. It's an identity matrix. Okay, this is a vector, identity matrix, and a vector again. It is understood that this has to be a transpose of a vector, right? If you think of it as a matrix, so this is also equal to A1, A2, A3. All of us are familiar with matrices, correct? Matrices and column matrices and row matrices. So 0, 1, 0. And that's B1, B2, B3. And that's the same as A dotted with B, right? Oh, that's just a notation. So this will be called a dyadic notation. We will use this a lot. And this here, another way of writing A dotted with B is AI BI or AI delta IJ times BJ. This will be the index notation. Just for convenience, because we will have vector operations often, whenever we want to do some operations, we will use this. Okay. Any questions on this? I'll encourage you guys to again go over the homework and try to pick some examples from it and try to work out. The first part of it is index notation, and the later part is the dyadic notation. So that's all for dot product. This comes out easy, and maybe I should. Look into it again. Okay.
So the so dyadic is just the vector notation of the identity matrix, right?
Dyadic means the unit
Yeah,
dyadic.
yeah.
So this is a unit dyadic, is nothing but delta IJ. So one is the matrix representation, and this is the, or if you want, if whatever that equal sign means, the different notations, right?
So it is the same as the identity matrix, right? I. So
It's exactly identity matrix, or maybe this is what you're asking, right? Yes,
yeah.
yes. Correct. But we will also have quantities like M. This will be a general tensor which has 9 components. Like, when they are not real, some random tensor, especially we will talk about stress momentum tensor. So that will have a structure like this. So it will be, for example, or the best example is phi of RT. This is the scalar potential, correct? Familiar? Scalar electric potential, maybe? Right, that's the voltage, like where that we measure for a capacitor. So that's a quantity related to the scalar electric potential. That's scalar. Next comes a field, vector field, right? So this is a vector field. So vector field potential, which is a field. So this is vector field or electric field, right? Scalar vector. A higher quantity in the tensor quantity will be when, so this is 1 component, 3 components. The next will be something with the 9 components, but it's a field. And you need to have an example associated with that, right? So let's say this is T. Okay. And have we come across anything that's a tensor field yet? And
Stress tensor.
Yes, for instance, I have not taught, but that's my promise that I'll introduce it, but probably, you have not seen it before, right? Unless you've taken a course similar to this, any other, yeah, I don't think you come across a tensor, field. Unless you do gravity. Gravity or, electromagnetism in the electrodynamic, sense. So this will be a stress tensor if you want. And that's what it is. And so this is 0, oh sorry, 1 component, 3 components, that's a vector, right? This has 9 components. And you can immediately say there is something with 3 indices, right? And then you cannot really write using a dyadic notation. That becomes a cube, right? So a vector, so there's a point, right? Then there is a vector, right? If this makes sense at all. This is clear, right? There's a vector. Right, so this is point, line, then this is 0 dimensions, that's 1 dimension, 2 dimensions will be a. That's clear? Maybe like this, correct? 0 dimensions, which is a point, a line. That's 1 index, 2 index makes it a plane, so that's a tensor of rank 1. Rank 2. So this is tensor of rank 1, rank 0. And next is, what's the next growth in dimensions? 0, 1, 2. Third, you want to come out of it. Cannot really draw it. Maybe like this. Maybe.
One day in the future, they'll make 3D.
Yeah, you get that. I mean, that's it. But still, you can draw it at least, right? I mean, if you're really good at the drawing, like you can at least draw it. Rank 4, you cannot, I mean, you can only imagine it in a certain sense, or you can always also imagine it. Yeah. So this is tensor of rank 3. One, if there are, if I runs from 1 to 3, that's 1 component, 3 components, 9 components. How many components here? Yeah. 27, right? And the next one will be 81, right? 81. So that's a 4th rank tensor. And the main difference between electrodynamics and general relativity, which involves gravity, is that gravity deals with space and time at a very equal or mostly equal footing. So you work with 4 indices. Here we are working with 3 indices. Mostly we will work with, I shouldn't say mostly we work with 3 indices. We're going to do special relativity very soon. And we will have the time index also. So we will have 4 indices. If we are working with 4 indices, a tensor of rank 4 will have how many components? We have 464. 4 into 4, 16, 16 into 16, correct? So it's 256, right? So it has, so when you deal with gravity, the tensor that you talk about typically is 256 components. And that's what typically gravity will involve. We won't be having to do with that. We will mostly be here, right? So that will be stress tensor, which will be 9 components and slightly easier to do. Okay, so that's our dot product, and that's sort of a list of what we are discussing, but we have cross products also, right? That's what I started this discussion. So for that reason, we introduce a new quantity. I think it's called Lewis-Cevita spelling. I always mess up. Is that correct? That's the symbol.
Yeah.
Is that correct? Okay, so Lewis-Civita symbol is like a Kronecker delta symbol. But this time it's a rank 3 quantity, so that's 3 indices. This is a tensor of which rank? 1, 2, 3. Is it a scalar? Is it a vector? Is it a tensor of rank 2 or is it a rank 3?
Tensor rank 2.
Rank 3.
Rank 3, rank
Three.
3 indices. So tensor of rank 3, and there is no summation anywhere. There is no repetition of indices. So these are 3 indices. That means how many components does it have? Right, if we are in 3 dimensions, it has 27 components. So I have now visualized that, right? So one way to visualize this is that each plane, right? So let's set I equal to 1, then it's a plane. So its components could be visualized as, so let's say this is I equal to 1 plane. So this is epsilon 1, 1, 1, epsilon 1, 1, 2, epsilon 1, 1, 3, epsilon 1, 2, 1, 1, 2, 2, epsilon 1, 2, 3, 1, 3, 1, 2. That's one plane in that cube. Set I equal to 2. And the second plane, so 2, 1, 1, 2, 2, 2, no. 2, 1, 2, 2, 1, 3, 2, 2, 1, 2, 2, 2, 2, 2, 3, and 2, 3, 1, 2, 3, 2, 2, 3, 3. And the third one, I will let you guys imagine. Okay, I'll be lazy. Okay.
But I don't know what it is.
Okay. It's okay.
No, I'm kidding.
Okay. Okay. Like the Kronecker delta symbol, the Lewis-Civita symbol is a known tensor. So I want to associate numbers to this. So how do I associate numbers to this? I say, if it ever repeats, epsilon ijk is equal to 0 if an index, or if I is equal to j, if I is equal to j, or j is equal to k, or I is equal to k. If any one of them repeat, that's equal to 0. Okay, that's one of the conditions, and you can see a lot of them 0, right? So this is 0. That's 0. That's 0. 1 repeats, 0, 0. That stays 0. Is that clear? And out of the 9 components, 7 of them went to 0. Just by putting that condition. It's the same, this is 0, that's 0, that stays 0, 0, 0, that stays 0. That's it. In fact, it helps to point out which is the one that's not 0. Write it. 3, 1, 1. 2, 1, 2. 3, 1, 3. 3, 1, 2. What is surviving, notice, are the non-diagonal terms. And they are opposite to, if you take the symmetry line to be the diagonal, that's opposite to that diagonal also. And here also. See, this goes away, this goes away, this goes away, this goes away. This goes away. So this, so what? So out of the 27 of them, only 6 survive, right? How do I? Now I have to tell, so just by one condition, I have thrown away 21 out of 27. Now I want to specify these 6 also. And for that, I say that this is equal to +1. Right, if it is a even permutation of epsilon 1, 2, 3. That means to say that I set epsilon 1, 2, 3 to be equal to +1. And then I swap any 2 of them. So let's say 2, 1, 3. I swapped it once, so that takes it, switch a sign. That's -1. Switch anything, I'm going to pick 3 and 1. So that's 3, 1. Switch the sign again. So that's +1. I can do 1 and 2 now. That's 1, 3, 2. That's equal to -1, and so on. And that gives me, so if this is -1, if it's an odd permutation. Of epsilon 1, 2, 3. And I said, somewhere here, I will also say this is equal to +1. So this becomes in our notation now, so this is 0, 0, 1, 1, 2, 3 is plus, so this is 0, 0, 1, 0, so 0, 0, 0. -1. Notice this is antisymmetric, right? It's an antisymmetric matrix. In the plane, it's actually a cube, right? It's a tensor. It's not in a matrix at all. This is 0, 0, 2, 1, 3. So that's -1 there, right? And so 2, 1, 3, right? -1 and 2, 3, 1. So it's +1. 0, 0, 0. And this one is 0, 3, 1, 2. 3, 1, 1, 1, 0. Okay, that's your Levi-Civita symbol in the with all the details for you, right? It's as detailed as you can get. But why are we doing this? Because the cross product is useful to write the cross product. Yeah. Okay, so let's think of a cross product, A cross B, and let's see. And if I'm thinking in terms of index notation, that's Ci, right? That's a vector. And A cross B, now I would like to write it in terms of indices. And it turns out that these indices or the Levi-Civita symbol is a convenient way to write the cross product. And it is written in terms of epsilon ijk, aj, and bk. There are how many free indices on the right side?
1.
Only one free index because j is sum, j is repeating, that means it's sum, k is repeating, so it is sum. So there's only one free index. On the left also there is only one free index. In fact, there's always a rule that the number of indices should match on the left and the right. It's like a vector can never be equal to a scalar, right? So in this equation, if I tell you that if let's say force. There's a real force in our Newton's law is equal to mass times, let's say. Energy or scalar, right? Some phi, right? That cannot be true because left side is a vector, right side is a scalar, that cannot be written. So you only relate similar quantities, which holds even in index notation. This means there is a summation in here. So let's try to find out what is C11. So C11 would be I has been set to 1, the first component of the cross product. Right? A cross U. What's the first component of the cross product? Can you do it from your head?
A2B3 minus A3B2.
Very good, right? 2 and 3. So notice what is coming in. The first component is coming out to be 2 and 3. Get rid of the 1. So do the cyclic property. So the first component it is A2B3 minus A3B2. The second component will be similarly
A3.
A3 cyclic,
B1.
right? 2, 3, and then
B1.
B1. 2, 3, 1, right? 1, 2, 3. So it is minus of A1 B3. And the third component will do the same thing. So that's a nice cyclic property you can think of in a cross product. We have the determinant property that we have. It's the same idea that works on the same thing. But let's see how this comes about. We are using a notation. So I have set I is equal to 1. That means I'm interested in 1 JK AJ BK. I have set one of the indices as 1. So the other two cannot be 1, right? It cannot repeat. That is, if I repeat it, it's 0. So it cannot repeat it. So J and K has to be 2 or 3. And again, 2 and 3 cannot repeat. So there are only 2 possibilities. So this has to be equal to epsilon 1, 2, 3 times A2 B3 plus epsilon 1, 3, 2 A3 B2. Is that clear how I went from this to this? As you get more experience, you will do this much more fluently, but first time, what you're doing here is that this is a summation. It's a repeated index. So you have to repeat, you have to sum them, but out of that sum, only 2 of them contribute. Out of the 9 pieces, J is sum, so that's 3. K is sum, that's another 3. There are 9 pieces in that sum. But only 2 contribute because there are only 6 of them that's actually non-zero. And out of that, only 2 are relevant in this. Is that clear what I'm arguing? Okay. Only if you work it a couple of times, it is easy to convince yourself. So go back and quiz, right? The number, go back home. Quiz. Right. Show this explicitly, right? Do that sum, write the 9 pieces and identify these zeros and put that zeros and show it. Is that clear what I'm asking? And it's pretty tedious, but just do it once in life. Like epsilon 1 to 3 is 1, so it is A2 B3 epsilon 1 3 2. I get this from starting, so it's minus A3, which is what we know as the first component of vector identity. So this seems to be a short form of this. C2 similarly is epsilon 2 JK AJ BK. Again, this is a sum. There are 9 pieces, but only 2 of them contribute. This time 2, 1, 3 A1 B3 plus epsilon 2, 3, 1 A3 B1. Again, 2, 1, 3, you get it from here with minus, so it's minus A1 B3, 2, 3, 1 plus A3 1, which is again correct that's supposed to be that, piece. Do the same thing with 3. It is 3 JK, AJ, K, that comes out to be epsilon 3, 1, 2, A1, E2 plus epsilon 3, 2, 1, A2, E1, so that's A1, E2 minus A2. So, overall, what we have shown is that overall, what we have shown is that whenever you have a dot product, as far as index notation goes, it is good to replace it immediately as AIBI, right? Or for that matter, if you have an index notation there, it's if whenever you see AIBI, that's a dot product. Same thing with cross product. A cross B is equal to the ith component of that, because now it's a vector. I have to associate a component to that. The ith component of that is epsilon I J K, A J and K. So that's your two things we have pointed out. Okay. This is all convenient and relatively easy if you're just working with vectors or even vector fields. But we have gradient operator we will be dealing with, and we would like to now do this for, let's say, first let's do again, repeat this for A cross B cross C. What is that equal to? Identity, that is an identity, right, where it splits into two. Right, back card, right, I see some of it. It's saying, so this is equal to the quantity that is in the brackets, you get two of them, so you have, let's say B and C, the negative sign B, and then rest of them is dotted. Let's see. Back and C is A dotted. I have not been careful with the position of B relative to C, or I have actually moved B across A, right? Sometimes that's not possible. For example, if you have a gradient operator, you cannot move past that. So you be careful on that, and we'll come back to that in a minute. How do we do this as far as let's say this is equal to D, right? That's a vector. So DI would be equal to, this is a cross product. This is epsilon I J K A J, right? That's a first vector. And the second vector is B cross with C. This is a mixed notation. I only partially moved it, right? I'm just using this to write that here, right? With me till now. Just the cross product is being done. But now I'm going to expand this further. That's epsilon I J K A J, but that's also S curl, so that's K. And now I cannot use the same index. So IJK I have used up, so I need more letters. So let's say M and N. That's DM and CN. There are how many indices here on the right side? 3, 4, 7, 9 indices on the right side, right? There are how many dummy indices?
2.
2. So that is J is a dummy, so let's say dummy, all right? Okay. So that is J, that is K is dummy, M is repeated, M is dummy, N is dummy, right?
Just I is the only.
I is the only free index, that means this is a vector. Even though there are 9 indices here, 4 of them are dummy. Right, 8 of them gone. So 9 minus 8, there is only 1 free index, so that's a vector. Even though it's built out of so many quantities, it's basically a vector. This is equal to epsilon, so notice that if I move epsilon ijk is equal to epsilon kij. Why? Because when I swap this once, I gain a sign. And then I swap again, I say another sign, so this is plus. Right, so this is the same as this because I need to swap twice. Even though earlier I was swapping numbers, I'm just now swapping the index itself. Right, so this is +1 -1. Is that clear? Any questions? Right.
So it is the permutation, we can directly bring the k to the first.
K to the first because I have to, oh, you're saying why not? So if I permute K and I, that is K, J, I. Right, that gives me a sign that's a minus sign. Right, and then I'm permuting again I and J, so that's plus K, I, J. But so that's either way, or what I was doing here is K and J permuting, and then K and I am permuting. So either way, so that's K, I, J. So if I do that here, so this is the same as K, I, J and K, M, N. Right, so that I've set it so that the first index is the same, right, and rest of them do not match. And there is AJ, BM, CN. Notice these are all numbers, right? Epsilon, whatever it is either +1, 0, or 1. So whether it is whatever A is, whether it's gradient or not, I can take it through it. I don't have to worry about it. So it will never be a problem that you can move this. Sometimes you cannot move A, B, and C between themselves. Like remember, gradient of A vector is not the same as A times a gradient vector, right? We will be introducing gradient very soon, so I cannot move them very freely. So I want to keep A, B, and C position as much as possible as it is if I'm working with gradient. We'll do an example very quickly for that. But now we need to know what this is, and this you have to actually evaluate. And it turns out that, again, look up in your homework, that this is equal to ijk, kmn is equal to delta. You notice there are 4 indices. Start with the I and relate it to M. Start with the J and relate it to N. And then swap them. Minus of delta IM, delta JM. This again, quiz. You don't have to evaluate this, that's elective, but look into the homework and see how it is coming. In the homework, I think it's a second problem. Just check it out how it is coming. Okay, so you don't have to evaluate this, that would be asking too much, but you don't have any homework of this course on Thursday, right? Maybe evaluate this. Okay, it's look up problem 2 in homework. Again, just have to remember quizzes for participation. If you get time, do it. If you don't get the time, don't do it. Okay. Is that clear what the question is?
But just evaluate number 2.
Yeah, number 2, yeah. Okay. So if I put that in here, that's IM JN minus IN JM. Multiply this with A J BM CM. That's equal to, remember what is the rule if you have a Kronecker delta. So that's good too. Now, so what is AI delta ij equal to? Right? The Lakshmi immediately said this is AJ. This is a good trick to realize. Notice that this survives only when I is equal to J. Right? The Kronecker delta by definition is an identity. It survives only when I is equal to J. And this is summed over, that's a dummy index. I don't care. So only when I is equal to J it survives. So basically, this is equivalent to saying a vector dotted with an identity matrix is equal to the matrix itself. Right? That's the same statement. Okay. Notice the similarity in this. A multiplied by the identity gives you a vector itself. A multiplied by the identity gives you a vector itself. Right. So that's this is the index version of this matrix already. If I use that in here, notice I'm having an M and an M, so I replace M with an I, right? So this is AJ, BI, and CJ. That's the first term. And I'm replacing N with an I, so this is AJ, BJ, CI. Is that clear how I did that? So I look for here. That's M. Right. When I put that, I can swallow the M and replace M with I. Replace M with I. IJ goes through that. That clear what is happening? Too many things, tiny small things that's happening. But with some factors it goes through. Questions? Ryan, clear, or should I elaborate on that?
No, yeah, it's clear.
Okay. If that's the case, now notice the free index here is this. And the free index here is C. Right? This is a dot product. Let A dotted with B times C, which is back cap, right? That's the same as this. And this one, if I can move, only if I can move C across B and A, then I can write this as B, A dotted with C. Only if I can move B and A through it, right? That's not always possible. You will see situations where it's not possible. So let me quickly do that. Okay. So now I'm going to do this again, but this time with a gradient operator. Notice that gradient of, if there is a scalar, A and a B is equal to A times gradient of B plus.
Dr. Shajesh, can you write it? in
Oh,
that
can you write it
point?
on this because you have, you're setting some. Okay, good point. Yeah, I want that space. Okay, remember, gradient of A times B, two scalars now, that's not really vector, I'll come back to that. This is equal to, I can operate on gradient of A. And this is the distribution property of your derivative, right? Or you can act on B. So both of this has this feature that a cross product has a distribution as a vector identity. And a gradient also has a distribution just because it's a derivative. So if there is a gradient in one of these quantities, there will be four pieces. Gradient will try to distribute like this. And the vector product will try to distribute like this, so there will be 4 pieces that will come out. And then, so let's try to see that, so this was scalar, so let's come back to the quantity, so let's say A cross B. Okay, so that's what we want to evaluate. Obviously, if we're taking the gradient, this must be fields, right? That must be a position dependence. If it's a constant vector, it will be 0. Like a derivative of a constant function is 0. So there must be position dependence in this. So we're talking about fields here. This argument goes through as it is, right, until here. And I immediately say that this is, let's say the ith component of this is the same as epsilon k. I can actually go all the way till here, right? So most of this goes through, and I get delta I m j n minus delta I n delta j m, except that now it is del j del j a m and b n. Okay. It's understood that this has to operate. This is a gradient, so it has to do this. Right, it has to distribute itself still. Let's do this replacement here first. So that's equal to del j a I b j minus of del j a j b I. Stop me if there are questions, and it's just tedious repeating the same ideas. But now I told you earlier that this will distribute itself into 4 pieces. And this is, as of till here, we have only done the distribution due to the vector product. Now I do the distribution due to the derivative. So I have to distribute. So this is j I times j plus a I times del j. Okay. But there is 2 more. J d I minus a j. That should be important in parentheses here also, but that's not confusing. Only when it is in the front, it's not clear whether this is acting only on this or on both. In electromagnetism, the components of a vector are usually numbers, right? The electric field, the component of an electric field is a number. When is it not a number? Can you think of a situation where the components of a vector are not really numbers?
Vector space,
Vector space, no,
or like a tensor.
no.
Vector potential.
No.
What was the question?
So the question is, if you have a vector, its components are usually numbers, right? When are they not numbers? What do I even mean by when it's not a number?
When it's a
Again,
function, you
multiplication.
mean?
When it's,
Like
or
a
when it
vector
doesn't
field?
satisfy 3 into 2 is 2 into 3. When it doesn't commute.
It's imaginary.
No, even they commute, right? Complex numbers,
yeah.
z1, z2 is equal to z2, z1.
Like a vector field?
I guessed it.
You said that.
Hmm?
What it is?
Operators, yeah, good. And where do they, yeah, when they are operators, good. Some more, a little more specific. Matrix, for example, or in quantum mechanics. Like in quantum mechanics, momentum times position cannot be swapped. Right?
Observer.
Like x comma p, is that familiar?
Yeah,
Right? This is equal to xp minus px, right? Is not equal to 0. In fact, it is equal to
IH.
IH bar. So this is position, that's momentum. Right, position is usually numbers in classical mechanics. Momentum is usually numbers in classical mechanics, but then you come and say that, no, I don't want this to be allowed. Like 3 times 2 is not 2 times 3. So that's quantum mechanics. You go say that there are no more numbers. So position and no momentum in quantum mechanics are no more numbers. Right, so they don't satisfy this. If you're doing quantum mechanics, then you have to be careful in moving things, but here they are numbers. In this course completely, all throughout, we will be working with electric field. Even if it's a tensor, they will be numbers, right? So I can move things around. If you're doing the same thing in quantum mechanics, if you're doing this vector product in quantum mechanics, you do that for angular momentum, if you remember, right? This doesn't go through easily. Right? Or maybe I should ask, I mean, I typically ask this, what is A cross A? Well, 0, it should be 0, right?
But not in quantum mechanics.
Not in quantum mechanics. Why not? Because this, if you remember, just that we did this permutation, right? This is nothing but its component, ith component. Agreed? Ith component here is equal to epsilon ijk times aj ak. Correct? The first component of this, let's say I is equal to 1, is equal to a2 a3 minus a3 a2. If these are numbers, they cancel out. But if they're not numbers, which is the case in quantum mechanics, they're not numbers, then they don't cancel out. Right? In fact, that's the identity is if you have angular momentum, the classic relation in quantum mechanics, angular momentum crossed with angular momentum gives you back an angular momentum. And there is an IH chart. Very non-trivial. Happens only quantum. This is usually written as Li. More commonly, this is written as Lij is equal to epsilon ijk Lk with an IH bar. That means its components don't commute. But if you write it as a vector, then you say this is equal to this, non-trivial. So otherwise, you always imagine 2 vectors in the same direction that's equal to 0. Cross product is not necessarily 0. Okay, but that's but the point here is that we are going to be in electrodynamics. I don't think all throughout the course we will have to worry about this components being operators. So I can do this freely. I can move things around. I move this to Bj. I can still not move it outside the gradient, right? I respect the gradient part of this. Gradient has to act on that function. This is AI J and minus this is also okay. I and this is change or remove the parentheses. Think of dot product whenever 2 indices comes together, there is a dot product, right? So this is the same as B started with gradient, that's a dot product. It leads to the idea of what is the interpretation of B dot as a gradient. This is the gradient in the direction of B. Like gradient in general is a derivative acting in any direction, right? But this is a derivative acting in the direction of B. So I choose that vector B and along that direction, pick 2 points and take the derivative if you want. Here, this is A times del dot with B. If it was a magnetic field, that's equal to 0, but here this is random quantities, right? So this is del dot with A times B, and this is minus of A. So the derivative in the direction of A. So derivative of B in the direction of A, right? Notice that language. Derivative of the quantity vector B in the direction of A. Okay. We started with the quantity that what is del dotted with del crossed with A? This is a cross, by the way, this ends here, right? The new thing on the line. I should answer what we started with. This comes out as dot product del I del cross A. And that's the same as del I epsilon I j k del j a k. Okay. Notice there are two quantities which are identical. And that means to say that, for example, one of the pieces could be epsilon 1, 2, 3, del 1, del 2, A3, right? That's one of the pieces possible in this. Epsilon 1, 2, 3 that is antisymmetric under a replacement of two indices. If I replace 2 and 1, it changes sign. So that's the same as minus epsilon 2, 1, 3, del 1, del 2, A3. But the gradient operator does not matter whether I write the derivative with x or derivative with respect to y. D by dx times d by dy is the same as d by dy times d by dx. Right? Always we deal with functions that always satisfy that, otherwise they are not integrable. So if we use that, now I can again flip this. So this is 2 and 1, so I have to just respect this. So this is minus epsilon 2, 1, 3, delta 2, delta 1, A3. But that makes me change this again. So this must be the same as this quantity, right? Because these two are the same. So that means to say that 2, 1, 3 has to be the same. That's not possible. So just by antisymmetry, this is not possible, right? Because this quantity is the same as this quantity, but this is not the same as this. So antisymmetry and symmetry doesn't go together. So epsilon I j k, if it ever comes with two identical vectors, I a j, for example, b k, it will not be satisfied because this is symmetric under the replacement of I and j. This is antisymmetric under the replacement of I and j, basically swapping. So together they cannot work, so that's equal to 0. And that's the reason why this goes away. Okay, I finished my
I
time.
think the last line is the vector component.
This
Okay,
one?
yes,
This is vector, yes, but this is a scalar, right? Dot.
no, it's vector component, not vector, because we used the I component of the vector.
No, right, this is a scalar, right?
Above that,
Oh, well, yeah, this is a vector, this is a vector I, right? So let's call it D here. Is that the question?
Yes,
So this was VI. And then I moved from I to the vector. It's like, yeah. Okay, so this was a crash course if you want. On index notation. Okay. Next time I will come and do dyadic notation, which will be more, slightly more powerful and intuitive in a sense, and we will do that. Here. That's it. Yeah, well, I too fast. Okay, so, yeah, catch up in a sense, yeah, okay, thank you. And look into the homework again, sort of what we, I think the first, many of the problems deals with all that we talked about.